Okay, welcome to the last flipped classroom video I'm going to make for the school year. This is the last section of stuff I'm teaching you. Yeah, so that's kind of epic, and it's probably gonna be really short. So first of all, let me just clarify the fact here that we are skipping to lesson 5 of the pre-calc unit. So there's a couple of things in there. So we've done 3.1. 3.2, and now we're doing 3.5. Long story about that you don't really need to know all the details about, but there's some stuff that might be in 3.3 or 3.4, and I'll tell you as we go what we're kind of skipping. So one of the things we're skipping is that question, but we can do the rest of them. So it's really close to what we're able to do, and yeah, again, long story. I'll tell you why and how this kind of links to Excel 2 when I see you. Okay, but yes, we are all about expected value. Oh, you notice that I crossed out the word distributions in this handout. That's the title of their unit. So okay, great. The distribution part is part you're going to do next year, but the probability and the counting, of course, is stuff we are doing this year, and part of that is expected value. Okay, so there's a. I hope this baseball context doesn't throw you up or throw you off the softball context. She's got a .666 batting average, which means she gets a hit 2/3 of the time. So if she has 5 at bats in a game, what's the likelihood she will get at least one hit? So we did an at least one here not too long ago in class. It was about the multiple choice answers, and you were counting like what's the probability that if you guess on all the multiple choice questions, what's probably you get at least one. And there was a trick for at least one. The trick for at least one is, well, because you could get 0 or 1 or 2 or 3 or 4 or 5 hits out of those 5 at bats. We want to find the probability of any one of these numbers of things happening. So let's just figure out everything except 0. That's a lot easier than trying to add up 1 or 2 or 3 or 4 or 5. We'll just add up for 0, or consider it for 0, and then take 100% minus that. So it's going to be 1 minus the probability of 0 hits. Okay, so the probability of 0 hits is pretty easy to figure out. She has to go up to bat the first time and not get a hit. She has a 1/3 chance of not getting a hit on the first at-bat. She has a 1/3 chance of not getting a hit on each of the at-bats, and there are 5 of them. So 1 minus 1/3 to the 5th power is, I believe, 80 over 243. I'm kind of cheating. Oops, 80 over 243. Let me actually check that. Glad I checked that. That was wrong. I was looking at the wrong part of the answer key. It's 242 out of 243, which is a pretty great probability. Yeah, 1/3 to the 5th power is 1 out of 243. And her probability of getting at least one hit is everything but that. In 60 times, okay, now this is kind of new, and this is a good... I'm doing this one because I want to talk you through this here. How many times did you expect her to get a hit? If she has a 1/3 chance of getting a hit every time, or sorry, a 2/3 chance of getting a hit every time she goes to bat. One way to interpret that 2/3 in the simplest terms is, well, if she goes to bat 3 times, you'd expect her to get 2 out of those 3. So we just kind of have to scale that up. How many would you expect her to get out of 60 if her expectation is 2 out of every 3? Well, notice I'm multiplying the denominator by 20, so I should multiply the numerator by 20. In other words, I would expect 40 hits. That's also the same as the calculation of 2/3 times 60, and that's actually the calculation we're going to be focusing on later in this lesson. That if the probability of getting a hit is 2/3, and you have 60 trials of that, you would expect 2/3 of those 60 trials to be successful, and that's the first explanation of what we mean by expected value. Okay, so the answer is 40, not 2/3 times 60. 40 is a better way to say that. Okay, we have this spinner, and it's going to land on either a 0 or a 4. How much money would you expect to win if you played the game 10 times? Well, we would expect to win half of the time we would get a 4, and half of the time we would get a 0. That kind of doesn't matter for anything. But half of the time we would get a 4, and out of 5 trials, we would expect to win half of those times. So I should say we should get half of the time, sorry, let me start over on that. I didn't like the way I explained that. Half of the time we'll win. So we will win 5 of the times, and we will get $4 each time we win. So we would expect to get 20. What if we played 100 times? Well, we would expect to win half of those times. Yeah, I guess I could have said it this way, half times 10. That's the way I did it up there with the 60. Half times 100. That's 50, and each one of those wins is $4, so we would expect to win $200. Okay, that's a better explanation. What would you expect to win per game? Well, that's kind of like saying, what would you expect to win on one spin of this spinner? Well, if 100 times we have expectation of winning $200, and 10 times we expect to win 20. What if we reduce that down to one time? You might guess we would actually expect to win $2. Now you're looking at the spinner and you're going, how in the heck am I going to win $2? Over the long run, notice 10 times should be $20, 100 times should be $200. It kind of stands to reason that one time would be, divide that back. It's only be $2. On average, per trial, that turns out to be $2 per trial on average we expect to win. So this idea of expected value, and here we are about to come to the definition. Expected value can be an unrealistic expectation. In other words, it can be between real expectations. It can be like if it's a number of people in some other kind of context, we can expect to have 2.3 people, or we can expect to own 1.7 cars and stuff like that. Because expectation is about an average over time kind of per trial thing. So yeah, expectation can be unrealistically decimally, but observed values cannot be. Observed values have to be real possibilities. All right, expected value informs us about what to expect in an experiment in the long run. And actually, I would even continue that to say per trial. What's the expected value each time you effectively spin the wheel? Calculate the expected value of the event, you do this. Now, this looks like a bunch of crazy notation, but all this is the well, does it have it explained here? Yeah, the probability that something happens, which is the PX business, times the value of what you get for sort of winning that. It's like the number of points times the probability of getting that number of points, and then you add them all up. That's what this thing means. Just means you're going to add them all up. This notation, kind of like some of the notations in this unit so far, is more complicated to read than it is to just do a bunch of times. Let's just do some. Okay, you're playing a game where you roll a die. You get $1 if the die lands on an odd number, and $2 if it lands on an even number. I'm just trying to move the page around, and I'm accidentally drawing. All right, what's the expected value for one roll of the die? Okay, so according to this formula we just learned, you get $1 for the die landing on an odd number. Actually, I'll make a table like the next one already shows. I think it's like, okay, they have number and they have outcome, and maybe we should say like probability of the number. Yeah, okay. So the number could be 1 or 2 or 3, and not 1 or 2 or 3. I know my odds and evens. 1 or 3 or 5, 2 or 4 or 6. The probability of that happening is half. The probability of that happening is half. The outcome is $1, or so the random variable outcome is $1 or $2. So we're gonna get $1 half of the time plus $2 half of the time. So there's each of these is the outcome of the random variable times the probability that it's going to happen, and we add all those up. So this is just 1/2 plus 1, which is 1.5 or 1.5 or 3/2. So if you play this game millions of times, you'd expect per roll of the die that you would gain $1.50. Because half the time you're gonna get 1, half the time you're gonna get 2. I don't think that's that crazy to kind of imagine that it would be between 1 and 2. In fact, it's exactly between 1 and 2 because 1 and 2 are equally weighted. But it is impossible to get 1.5 on any one spin. 1.5 is the per roll average win in the long run. Okay, next one, same kind of idea. There's the table for it. We've got the 4 outcomes and the 4 prizes. Oh, there's win and pay. Oh gosh, it's like some of these are negative. Can I just call this positive and negative? That might be a lot easier to deal with later. What's the expected value? Okay, so is it 4 equally spaced? I'm guessing they're all 1/4. Okay, this is $2 times a quarter minus $2 times a quarter, I said, minus $3 times a quarter, plus $5 times a quarter. If I do all of that math, I'm just going to see if I've got that right here. I do. It's 50 cents. So, yeah, per play of this game, you expect on average to gain 50 cents. Yeah. Would you recommend playing this game if it costs $1 to play? Well, probably not. If you're going to only win 50 cents on average, I would say no, because $1, basically because you're paying $1 and you're getting 50 cents back is still a loss. All right. We're going to talk about fairness and is it fair for the player, or what they call the house. In kind of these kind of games, because a lot of this is actually about if you're trying to design a game, or if you're trying to fool someone, or if you're you're potentially being fooled. How do you figure this out? I think it's a really good skill to have. All right, new game called Double Spin. The player, it's a really creative name. The player gets to spin a spinner twice, but wins only if the same amount comes up both times. The $100 sector is 1/8, and everything else is a quarter, so this must be 3/8. Okay. But, whoops, not 1/4, 1/8, 1/4, 1/4. Okay. So the probability of getting 0, well, I'll fill that out last. The probability of getting 1, you have to get the same thing twice, right? So you'd have to get 3/8 times 3/8 for that, which would be 9 out of 64. Oh my gosh, okay. I can kind of square these in my head. I'm running out of space. I'm going to run out of space already. Actually, if I make this bigger. This one's 9 out of 64. The $5, I have to get the quarter and the quarter, so that's 1 out of 16. Let's call that 4 out of 64. That's going to be easier to add later. The 10 is the same. I have to get the 10 twice, which is 1 out of 16. The 100, I have to go an eighth times an eighth, which is 1 out of 64. And so the rest of this now, this is like a 1 minus kind of situation. The 0 is easy to figure out because I can just subtract all the rest of those from 64, and I get 46 out of 64. Great. So what's the expected value? The expected value here is, it's, what am I usually doing? Yeah, I'm doing the x first. Yeah, so the 0 times 46 out of 64. That seems silly, but I'm going to write it just to have the formula be complete there. 9 out of 64 plus 5 times 4 out of 64 plus 10 times 4 out of 64 plus 100 times 1 out of 64. The answer key I'm looking at says that's going to be $2.64. So that's... Oh, as a fraction, it was 169 over 64. That's a winning game if it costs you up to $2. What makes this game fair? I was just kind of talking about that before. If they were going to charge the player $2.64, they would kind of break even after millions of plays. So I would say what makes the game fair. We can talk about this in class, but like say expected win equals cost might be one way to say that, so that no one in the long run, no one's going to benefit one way or the other, whether you're kind of in charge of managing this game or you're the player. In the long run, it would be fair if you, in the long run, we're supposed to have the same amount of money. Is it a fair game if it costs $2 to play? No, because you would be advantaged if you only had to pay $2 in the long run. You're gonna make money at this game. You would expect to gain. So it's better than fair for you. More than you pay to play. So it's a good game in your favor. Most casinos and or whatever, but people who set up these kind of games are going to try to take money from you, and they try to make them look attractive. They try to make them look like, oh, I just have to do that and I'm going to win money. But they know they do it in such a way that they know in the long run you're going to lose to them. But this game, whoever designed this game was, if they're only going to charge $2, they are going to lose money in the long run. I did, because I'm doing it a little bit differently here, or I see it a little bit differently here than just kind of in order than they do it in AP Stats. There's like the outcome, and then there's the random variable outcome, and then it's a probability. Okay, long run. Okay, person plays the crawl game with a pair of coins. 2 heads appear, then $10 is one. If a head and the tail appear, it's $3. Oh, we already know about this probability. If 2 appear, it's $5 lost. I think it's a good idea to make this little table. So there's the outcomes and there's the probability of outcomes. The outcomes here are, let's do that. How did I do it before? I want to make it look exactly the same. So let's talk about the coins first. The coins, let me make a little more room here. The coins are going to show, I put the probability at the bottom. There's 3 of them, right? We'll call this X. So the X is the $10 one, or the $3 one, or the $5 lost. So this is heads. This is tails. This is heads, tails, or tails, heads. The probability of heads is 1 out of 4. The probability of tails is 1 out of 4. The probability of the middle thing happening is 1 out of 2. And we've talked about that like 3 lessons ago. So hopefully that was easy review. What should they charge? Well, let's figure out the expected value first. The expected value is 10 times a quarter plus 3 times a half minus 5 times a quarter. That all comes out to 275 by the answer key I'm looking at. So I'm really cheating. I'm getting lazy here. This is the very last video that I'm making for you. So really, if they're the organizer, say this is your service club and you're trying to design this game so that your service club makes money, but people have fun, and as long as you charge $2.76, you're gonna make money. The answer key I'm looking at says 375. Oh, it said, well, that's why, because it says $1. I missed that. If they want to make an average per game, they should charge $3.75. That's a weird amount of money. They should probably charge $3 if they want to keep more people playing, or charge $5 if they want to make a lot of money fast. Anyway, they're specifying they want to make $1 per game on average, then they should charge $3.75. Okay, we are almost done. Just 2 little more examples left. 15% of otters in large aquatic community are infected with a parasite. In a sample of, I'm going to part B. In a sample of 500 otters, how many do we expect? Expected value here, I mean, it's the same term, expected value, but the calculation here is a lot easier. So, gosh, do I want to tell you about the AP stats? The AP stats way to do this, we call it N times P. N being the number of trials, and P being the probability of success. And what is it? 15%. It's 15% of 500. Which is 75. Now, if that came out to a decimal, I would leave it as a decimal, and I would not, I'd round it to 3 decimals, but I would not round it to the nearest whole number of otters, because this is an expected value. Okay. If 3 coins are tossed, what's the chance they all fall on heads? I think you are pretty good at this by now. I need the probability of, in notation, tails, tails, tails. No, heads, heads, heads. Didn't take me long to forget that. First one has to be heads, second one has to be heads, third one has to be heads. There's no other way that can happen, so that's just 1 out of 8. And if 3 coins are tossed 200 times, how many times do you expect them all to land on heads? It's the same kind of thing as before. We're going to say the N. You know what? I'm going to go ahead and teach you the N times P notation. That is not on the theorem sheet, but it's pretty darn easy to just reason your way through that. Well, we expected, if we're doing it 200 times, we expect 1/8 of those times to work out this way. Then we'd say 200 times 1/8. That's the number of times we expect. Again, it happened to work out to a whole number, but if it was a decimal, we would leave it decimally. Okay, congratulations, made it to the end of my last video. I will see you soon.